Welcome to this presentation on the monoid structure of the power set of a group. In this presentation, we will define the power set of a group G, define a monoid, and show that the power set of a group G naturally inherits a monoid structure from the group structure of G. This will be the content of part 1. In part 2, we will show that the set of all normal subgroups of G forms a commutative submonoid of the power set of G. So let's look at the power set of group G. First, just let G denote an arbitrary set. Then the power set of G, denoted curly P of G, is defined to be the set of all subsets of G. We now say that a monoid is a pair M, star, where M is a non-empty set and star is a binary operation from M to itself satisfying the following axioms: the associativity axiom and the identity element axiom. These are directly taken from the axioms for groups. All we're missing from the group axioms here is the inverses axiom. So the associativity axiom says that if we find out what x star y is and then star that with z, that's the same as having x and starring that with whatever y star z is. And the identity element axiom says that there exists an element that we call 1m in our set M, such that x star 1m equals 1m star x equals x for every element x in M. Now, assume G is a group and H and K are subsets of G. Now note that we're not imposing any conditions on these subsets. They don't have to be subgroups, and in fact they could also be the empty set. We now define H star K to be their product as group subsets. So this HK here just denotes the collection of all of the elements of the group G of the form HK, where H is an element of H and K is an element of K. So this multiplication here is multiplication in G. If either or both of these subsets are the empty set, we just take their product to be the empty set. We note that star is clearly a binary operation on the power set of G because it takes two subsets of our group G and takes them to another subset of our group G. We now show that this star here is associative. So let H, K and L be subsets of our group G. Then H star K, all starred with L, is defined as the subset of G of the following form: the elements H prime in the product HK multiplied by the elements L in the subset L. This is all occurring within the group G. We note that this, by the definition of this, equals the following. Now we apply the associativity axioms in our group to obtain the following. And now we note that here the set of all elements of G of the form KL, where K is in the subset K and L is in the subset L, is simply the collection of elements K prime, where K prime is in the product KL. Once again, this is just following this definition. But this is exactly the same as this. So we've shown that this binary operation star is associative. We have the subset of G consisting of the identity element of G, so the trivial subgroup of G, satisfies H star of that trivial subgroup equals the trivial subgroup starred with H for all subsets H of G. This is very easy to check from this definition. And all of this says that the power set of the group G, equipped with this binary operation star, has the structure of a monoid. And this follows because we've shown that star is a binary operation on the power set of G. So we've shown this part. We've shown that it's associative, and we've shown that the trivial subgroup of G satisfies the identity element axiom. In the next part, we will show that the collection of all normal subgroups of G forms a commutative submonoid of this power set of G.